Welcome to Spring LIB.
Our question is broken into part A and part B, but for both, we're going to consider the fact that the width of a single slit is doubled and the intensity of the light passing through the slit is doubled. So for part A, it says, show, however you can, that the intensity at the center of the screen increases by a factor of 4 if you double the width of the slit. Okay, so let's let the amplitude here equal capital A. So we can say capital A is amplitude, and the amplitude is equal to N, where N here is the number of wavelets with the amplitude energy E. So it would be N number of wavelets times the energy E. So since the central intensity, I, goes as the amplitude squared, so I goes as the amplitude A squared. So this goes as N times E squared. And let's not set it equal. Well, let's at least show that it's proportional. There might be some other constant values in there and stuff like that, but we don't care about that stuff. So we'll just do that to show that they're proportional. Okay, so, but we want to show that that the intensity increases by a factor of 4 if we double the width of the slits here. So doubling the size of a slit means doubling the number of wavelets. Okay, so the number of wavelets N is proportional to the width of the slit. We'll call that D. So if you double D, you double N. So 2 times N times E gets squared for intensity. So if you do that, then this goes to 4 Ne squared, or 4 times the original intensity, because we said that the original intensity was proportional to Ne squared. So you do end up increasing it by a factor of 4. And this is what we were trying to show. So we can box that in as our solution. And this is part A. Part B says, explain why this does not violate conservation of energy. Okay, so while the intensity increases, the central maximum narrows. So that's part 1 of why this is true. So let's just go ahead and type this out. We can say, while the intensity increases, the central maxima narrows. Okay, well, how can we show this? Well, it's because the sine of the angle of diffraction, theta, is equal to lambda over d. So you increase d, then that central maxima is going to narrow. Therefore, the energy is conserved. So you increase the intensity, but you're narrowing the central maxima, so the energy ends up being conserved. So we can say thus energy is conserved. And that would be your solution to B. You could go ahead and box all of it in if you would like.